Hi everyone, the topic for today is energetics. So first of all, we'll talk about heat capacity. Now, heat capacity is a measure of a material's ability to absorb energy for a given increase in temperature. So what that means is different materials have different abilities to absorb energy. So a substance with a large heat capacity, such as water, can absorb a lot of energy before it raises its temperature. Substances with a small heat capacity, such as aluminium, when you apply heat to it, it will heat up rapidly. It'll increase temperature rapidly. So it has a small heat capacity. This equation here, Q equals C delta T, refers to the energy. C is the heat capacity, and delta T is the change in temperature. So a substance that has a large heat capacity means that you would have to supply a lot of energy in order to increase that delta T. So let's have a look at an example. A piece of metal has a heat capacity of 2.07 joules per Kelvin. What quantity of heat must be supplied in order to change the temperature of the metal from 22 degrees Celsius to 45 degrees Celsius? So, just using that formula, we put in our 2.07 joules per Kelvin for our heat capacity. We put in our delta T, which is going to be the final, take away the initial. Remember that the change is always the final minus the initial. So we put those values in. Now here I've converted the temperatures to Kelvin in both cases. You'll see in a minute we don't really have to do that. But just as an example, we get this value, so 47.6 joules. That means that I would have to put in 47.6 joules of energy to this material in order to raise that temperature from 22 degrees Celsius to 45 degrees Celsius. Okay, and then that would be 48 if you're going to use 2 sig figs, which we should, because the temperature was 2 sig figs. When we have delta T, there is no need to convert from degrees Celsius to Kelvin, and the reason is because to this 45 I add 273.15 when I'm converting to Kelvin, but I also add 273.15 to this value, and because there's a subtraction here, it'll be 273.15 here plus minus the 273.15, and so you get rid of that term. So the difference between these two is the same as the difference between these two. So this is only appropriate for delta T, not T. So it's only in these special cases where we have a change in temperature that we can neglect the need to use Kelvin. If you're using, say, the ideal gas equation and it calls for T, you must use Kelvin still. It's only for delta T. So now we come to the term specific heat capacity, and what this means is that we look at it on a per mass basis, sometimes on a per mole basis, but for this course we'll just look at it on a per mass basis. So the normal heat capacity, which was the capital C that I had before, would just be measuring the material as it is. But you can then look at it on a per gram basis, which means you'd have a look at the material, work out how much it weighs, and then you could see what it would be, heat capacity on a per gram basis. The specific heat capacity is more relevant in a lot of chemical reactions, but there are other situations where just the heat capacity is useful. So obviously the more material we have, the greater the heat capacity, and so then we can just look at it on a per mass basis. The specific heat capacity of water is 4.184 joules per Kelvin per gram. So that means that you have to have, if you have 1 gram of water, you have to have 4.184 joules of energy in order to increase the temperature by 1 Kelvin, or 1 degree Celsius, same thing. So, so just to reiterate that, if you had 1 gram of water, you would have to supply this much energy in order to get that temperature to increase by 1 degree. If you had to increase it by 3 degrees, then you'd have 3 times this amount of energy as a requirement to do that. So let's have a look at calorie. And so because this is so widely used, in the US we call this quantity of energy at 1 calorie. Okay. Now notice how this calorie is spelt with a lowercase c. a calorie with a capital C is 1,000 times this number. So it would be 4,184 joules. So 1 calorie, again with a capital C, is equal to 1,000 calories with a little c, which is the same as 1 kilocalorie. Often calories just abbreviated with cal instead of writing the whole word out. And so, everyone's familiar with food labeling, which has the calories. They're actually the capital C calories. So if you've got some chocolate bar that's 100 calories, that's actually 100,000 of these normal calories, if that makes sense. Okay. So a chemical reaction in a solution causes the temperature to rise from 17 degrees Celsius to 28 degrees Celsius. The mass of the solution is 202 grams. What is the energy released by the reaction, assuming a specific heat of 4.184 joules per Kelvin per gram? So we go ahead and look at this. So a specific heat capacity, just using a little c, is here. And so I put in the mass of the water, or the solution, times specific heat capacity multiplied by the change in temperature, which was 11 Kelvin, going from 17 degrees Celsius to 28 degrees Celsius. Okay, this gives me this value, and so then I can report that in kilojoules. You don't have to convert to kilojoules, it's fine just to leave it in joules, but that will be 9.3 to go into 2 sig figs. Again, because our temperature is 2 sig figs here. So another example, what is the final temperature when 30 grams of water at 100 degrees Celsius is mixed with 50 grams of water at 20 degrees Celsius? So this might seem like a difficult problem, but basically we're comparing Q hot to Q cold. Now Q, I should have mentioned before, is energy, and I should have emphasized that it's not temperature. There's a difference between heat and temperature. Heat is a measure of energy. Temperature is just a measure of how hot something is. So heat is referring to energy. So in chemistry and in physics, when you hear the term heat, don't think in terms of temperature. Heat is energy. So I've got the Q hot, the energy from the hot water, and the energy from the cold here. Now one's the negative of the other. It doesn't matter which side you put that negative on, but one has to be the negative of the other, because the flow of the heat is going to go from the hot water into the cold water, and so there's a directional change there. Again, it doesn't matter which side you have as long as they're opposites. So then I put down the mass of the hot, the specific heat capacity of the hot, the change in temperature of the hot, the mass of the cold, specific heat capacity of the cold, and the change in temperature of the cold. So these are going to have the same final temperature. So I put in the T hot final, T hot initial, T cold final, T cold initial. So they're going to have the same final temperature. Okay, obviously because they're going to come to equilibrium. And so I can just change these terms into TF. And then I go ahead and start expanding it out. And so then I can rearrange it. And as I rearrange it, I'm going to put my terms with the TF on the left here, and my terms with the T initials, whether hot or cold, the initial temperatures on the right, and because I'm trying to find the final temperature, so I want to try and isolate that. And so then all I've got to do is factor out the MH and the MC. So I take that out the front, factor that out, and then I divide through this side by that MH plus MC. If the math is a bit hard, please take the time to write it down on a piece of paper and derive it yourself. I know it looks complicated, but after you get familiar with it, it's really not that hard. Some of you might find it easier instead of working with letters all the way through. For me, it's better to work through with the letters. But if you want, at these initial stages, you can put in the mass of the hot water. You can put in the mass of the cold if you prefer to work with numbers. The heat capacity with the hot and the cold will cancel anyway. But then you can put in here your initial hot temperature, which was 100 degrees Celsius. You can put in your initial cold temperature, which was 20 degrees Celsius. You can put those numbers in if it's easier to work with the numbers rather than the letters. So then that leads us with putting the numbers in at the end, in my case. And so after I do all that, I get my temperature there, which happens to be 50 degrees Celsius. Okay, so again, make sure you can derive this methodology of working stuff out. Enthalpy. So enthalpy is a measure of the heat that comes off the reactions. So with reactions, we either have heat released or absorbed. Now, reactions that absorb heat are called endothermic, and reactions that release heat are called exothermic. This is the one that's easier to remember, because releasing heat, you can think of like exhaling is releasing, air. Exhaust, again, releasing gases from combustion. These sorts of things. So, endothermic is just the opposite. It's absorbing heat. This is what the energy diagrams look like. So if we have an endothermic reaction, we have our energy on the y-axis, and our reaction coordinate, RxN, is just an abbreviation for reaction. So a reaction coordinate just basically means time, or just the way the reaction is progressing. So we have a look at the energy states of our reactants compared to our products. We see the products are higher in this case. And the change, so we forget about the hump. We'll talk about the hump later. But basically, you look at the difference between the states of the products and the states of the reactants. And that gap there is the change in the enthalpy. So for an endothermic case, it's a positive value. Remember, change always means final minus initial. This is a larger value. The final value is higher, so when I subtract the initial, it's going to be a positive value. In the exothermic case, the reactants are actually in a higher energy level than what the products end up being. So the products are going to have a smaller value than the reactants, and so when you have the smaller value take away a larger value, you get a negative delta H. So just remember, exothermic delta H is negative, endothermic delta H is positive, and this is what the reaction energy profile looks like. Again, just ignore the hump for the time being. So let's have a look at some bond energies. There's a couple of ways you can look at the enthalpy of a reaction, and one of them is to look at the bond energies. So in the bond energies, we can see that a hydrogen-hydrogen bond requires 431 kilojoules per mole of energy to break. A chlorine-chlorine bond is 239, an HCl bond is 427, a CCl bond is 327, a CH bond is 410, a CC bond is 335. So what is the net energy released from the following reaction? So if we have a look at this reaction here carefully, we see we have a CH4. That's a carbon with 4 hydrogens bound off. Okay, and we have a Cl2, which is just a chlorine-chlorine with a single bond. So if we compare this molecule to this molecule, we can see that we have removed 3 of the hydrogens. Sorry, this is a mistake here. This should be CH3Cl. Okay, so in order for it to balance, so we've removed one of the hydrogens to give the HCl, and we split up this chlorine-chlorine bond, and one of the chlorines has gone with this carbon. So it would be a central carbon surrounded by 1, 2, 3 hydrogens, and then a chlorine bound off the central carbon as well. So when I'm looking at the way that this is broken up, I'm going to have to consider a CH bond being broken. I'm going to have to consider a Cl-Cl bond being broken, so I'm going to have to consider this energy here. I'm also going to have to consider a carbon. These other 3 hydrogens haven't had any interaction, but I'm going to have to consider the carbon and the chlorine bonding together. So that would be this value here. And I'm also going to have to consider the hydrogen bonding with the chlorine. So it might be useful if you're having trouble thinking about these structures, is to maybe do a Lewis structure or something for this one with the carbon in the center, 3 hydrogens and a chlorine around that central atom. Okay. So the other important thing here to remember is that bond breaking is endothermic. Bond making is exothermic. So it means that if you've got a molecule like this, so there's 2 atoms in a molecule like this, if you want to break them up, you've got to have enough energy and enough shaking of the molecules till it suddenly just can't stay together and it breaks. You've got to supply energy for that to happen. If, on the other hand, you want to make a bond and you've got two molecules that are, or two atoms that are vibrating like this, in order for them to come together, they're going to have to stop vibrating so much. And so the only way they can do that is to release the heat. And then when they settle down a bit, then they can form that bond. So in the case of this CH bond, it's broken, so I have to supply 410 kilojoules. That data came from the previous sheet. So I have to supply 410 kilojoules of energy in order to break this bond. The CCl bond, again, is broken, and so I have to supply the 239 kilojoules. The carbon-carbon chloride bond, or chlorine bond, is formed. So that means that in order for that carbon to bond with the chlorine, it has to release 327 kilojoules. And so that's, to release it, we put a negative there. It's got to lose it, so it's a minus. The HCl bond is also formed, and for the same reason, it has to release 427 kilojoules of energy. Okay, so all we do after this is add them up. So you add the energy that had to go into it, and you subtract the energy that had to go out of it, basically. And so then you get a delta H, which is minus 105 kilojoules per mole. Or sorry, just kilojoules. This is an exothermic reaction because it has released the heat. The original question said how much heat is released, and that would be 105 kilojoules is released. Okay, so another way we can look at chemical reactions, instead of looking at the actual bond energies that are involved, we look at what's called the heats of formation. So elements in their normal states have enthalpies of formation of 0. So if you have, say, O2, its enthalpy of formation, so this is enthalpy delta H, F being formation, this superscript here of a O or a 0 indicates the standard state. Okay, so the standard state is 25 degrees Celsius and 1 bar of pressure. 1 bar is about 1 atmosphere. Okay, or 101.325 kilopascals is 1 atmosphere, so it's a little bit less than 1 atmosphere is what 1 bar is. 1 bar is 100 kilopascals. So, and you might want to look up Google standard state if you want to see the full details there. But a standard state for O2 is 0, because O for oxygen normally exists as O2 in our everyday world. And the same with sodium. The standard state is going to be sodium solid, because that would be the state that would be a standard state, rather than sodium gas or sodium liquid. And so this compound here, C2H2, which is acetylene, is not in its standard state. The standard state would be a carbon solid and hydrogen gas, for instance. But the molecule itself isn't in a standard state. You have to have elements on their own. So for this reason, the delta H of formation is going to be some non-zero value. In this case, 227 kilojoules per mole. Again, because it's not in its natural state. Okay, so the enthalpy of a reaction, you can look at, by the way, those standard states for the elements being 0 are what everything else is based off. So that's just set as the arbitrary number, if you like. That's just set as the 0 number. And so that all these other enthalpies of formation from the compound are observed by looking at the heat that is released or absorbed from forming those compounds from their constituent elements. Okay, so the enthalpy of reaction is always the sum of the delta H of formation of the products, take away the sum of the delta H formation of the reactants. So if we have a look here with their compounds, we've got acetylene again, plus 227. Water, the heat of formation of water is minus 242 kilojoules per mole. The CO2 gas formation is minus 393 kilojoules per mole. So you want to calculate the delta H for the following reaction. The acetylene, the oxygen reacting to give you carbon dioxide and water. So notice in this table we don't have the delta H of formation for oxygen. We have it for acetylene, carbon dioxide and water, but not for oxygen, because it's a 0 value, and you are expected to know that. So when I do the math on this, because the reaction has 2 acetylenes and 4 carbon dioxides and 2 waters, I need to be cognizant of these numbers, these stoichiometric mole ratios here. I need to carry these into my calculation. So when I look at the delta H of the reaction, I'm looking at my enthalpy of formation of my products, take away the enthalpy of formation of my reactants. So my products were the carbon dioxide and the water, and as I said, I've got to carry that stoichiometry in there. So there's 4 carbon dioxide, so it's 4 times the delta H of 1 carbon dioxide plus 2 times the delta H of the water, and then take away the reactant part. So the reactants, just so you don't get mixed up with the negatives, it's often a good idea to put parentheses around these terms so that when you have a negative multiplied by a negative, you don't get confused and accidentally write another negative instead of a positive. So so here I'm looking at the sum of the reactants, and then I'll subtract that from here. So the sum of the reactants is 2 times the delta H for the acetylene plus 5 times the delta H for the O2, and we know that the O2 here is 0. But I'll put in all the values, so this would be the delta H formation for carbon dioxide, delta H formation for water, and then I have my delta H formation for my acetylene, and here for the oxygen, which is 0 anyway. And so I get this number total. You might want to put that into your calculator and make sure you get that value. So in a question, you may have to determine the enthalpy per mole, and in this case, you just divide by the enthalpy by the number of moles. So what can happen is you can get a question where it says you have, say, 25 grams of acetylene, and you get 25 grams of acetylene, and you have a certain amount of heat released, and it'll say what's the enthalpy per mole. And so you have to work out how many moles 25 grams of acetylene is, just using number of moles equals mass over molar mass. Then when you have that number of moles, you look at the enthalpy that's being produced and you divide it by those number of moles, and then you have on a per mole basis. So heat to formation refer to forming a substance from elements in their normal state, as I've said. Which correct equation is correct for the enthalpy of formation of SO3 gas? So if you want to look at the enthalpy of formation of SO3 gas, we've got to remember that we're dealing from the elemental states. And so this one is definitely wrong because it's got SO, okay, plus O2 gives SO3. SO2 again is not in its elemental state. Again, this oxygen here is not in its elemental state, its normal natural elemental state, I should say, because oxygen doesn't normally exist in nature as O without any other oxygens bonded to it. So that's the reason this one's incorrect, as well as this one being incorrect. Again here, our SO2 is wrong. D is correct because we have S in its solid form, which can be found in nature. We have our O2 in normal form, and we get an SO3 gas. Okay, so that would be the equation that is correct. Hess's law. Equations can be added and subtracted along with their heats of reaction. So Hess's law is a way for us to determine the enthalpy of formation for, well, not formation, but enthalpy of reaction for a certain reaction just by looking at similar reactions that can be added to give that reaction. So the best way to understand this is to look at an example. So for this reaction, you want to determine the heat of reaction for carbon solid reacting with water to give carbon dioxide and some H2 gas. So we don't know the delta H for this top reaction. We do know the delta H for this other reaction, which is carbon plus O2 gives CO2 minus 393.5 kilojoules per mole is the delta H. And we know it for H2 and O2 giving water, and we have this delta H. So these are two reactions that we do know. So what we do is we write out those two equations that we know, and we label them 1 and 2. Okay, and we really want this equation, which was the one with the unknown, and so we compare this equation that we want with these other equations. And I can see from this equation that H2O is a reactant, and carbon is reactant. And so I'll look in these other equations and see where is carbon a reactant. And so here, or carbon present. So here carbon is present. And so I know that I'm probably going to have this equation as it is, because there's one carbon and there's one carbon that's going to be added. Then I'll look at water, and where does water appear in these equations? Water appears up here. So water, if I'm going to have an addition of these two, I'm probably going to have this one flipped around, so that I'll rewrite it so it would go backwards. H2O goes to O2 and H2, half O2 and H2. See, so I've got to consider that, and then I have a look at the carbon dioxide. Carbon dioxide is a product, and here it's a product, so again that reaffirms that equation 1 will be left the way it is. Equation 2 has the H2 as well, and so that tells me that this here it's a product, here it's a reactant, that I do indeed probably have to flip these around in order to add them. The other thing I have to do is, stoichiometrically there was 2 waters and 2 hydrogens, and so on this equation 2 there's 1 water and 1 hydrogen gas. So what I really need to do is to reverse equation 2 and multiply it by 2 as well. Okay, so I need to keep reaction 1 the same, but I need to add it to equation 2 reversed and multiplied by 2. So I'll do that. So this is equation 1 left as is. Equation 2 here is reversed, so that what was a reactant is now a product, and what was a product is now a reactant. I've also multiplied all these things by 2. So here, so there's 2H2 as a product now. There's 2 times a half, which is 1 O2 as a product here, and the H2O is also multiplied by 2. So when I do that, you can see that when I add it all up, I'm going to have, I add basically everything on the left hand side of the arrow, on the arrows I should say, I add up, and everything on the right hand side of the arrows I add up and place them on the right hand side. So here I've got carbon plus O2 plus 2H2O, carbon, O2, 2H2O. Then on the right hand side I've got carbon dioxide, 2H2 and O2. And so I've got O2 appearing on the left and on the right, and so I can cancel those off. And so I'm just left with this equation. Now I've got to consider my enthalpies. So here again, look at the enthalpies. This one will stay the same because the equation didn't have to be manipulated in any way. This equation had to have it reversed, so the sign will change, and it also had to be multiplied by 2. Okay, so this is what I'm doing here. So now we get our delta H of reaction. Is the delta H1 again stays the same, but I have to multiply by 2 the delta H2. So so it's 2 times minus being because I've got to change the sign. The minus is just telling me I had to reverse the reaction, and it already had a negative value anyway, so just put that in there, and then when you do all that you get 90.1 kilojoules. Okay, so now we look at entropy. Entropy is a measure of disorder in a system. The entropy of the universe is always increasing. So the entropy of the universe is really a summation of the entropy of the system where a reaction is occurring, and the entropy of the surroundings. We won't go into detail of that, but basically the entropy of the universe is always increasing, and there's a lot more detail we could go into with entropy, but it's beyond the scope of this course. So what we really do need to know though is that entropy is a measure of disorder, so how random things are. Entropy is favourable. Reactions prefer to have more disorder. Okay, so if you think about gasoline burning in your car engine, what's going on is those hydrocarbons, so they're carbon and hydrogen molecules, are being reacted with oxygen and forming smaller, more sparsely, not sparse, I guess, more widely distributed molecules of more disorder, such as carbon dioxide and water, and so there's much more of them. Okay, so which reaction has the greatest increase in entropy? If we look at N2O4 breaking up to N2 and O2, we see that we have 1 gas molecule is forming 1 plus 2 is 3 gas molecules total. So that's a very favourable entropic result here. B, we have C2H6 with 7.5 O2. So total, we'd have 1 plus 7.5, which is 7 halves, sorry, which is 3.5. So there's a total of 4.5 gas molecules on the left, and on the right we have 5. So there's been a slight increase in entropy from 4.5 gas molecules to 5 gas molecules. This one we have the carbon monoxide with a half O2, so there's 1.5 molecules here, gives us 1. So that's actually a decrease in entropy. We've gone from 1.5 down to 1. And here we've gone from 3 down to 2. So again, a decrease in entropy. So so entropy doesn't tell us the whole story, and we'll get to Gibbs free energy in a minute to predict, whether a reaction is going to be spontaneous or not. But entropy is something that's good, but enthalpy considerations can also affect the reaction, whether it's going to proceed or not. Okay, so the answer is A, because of going from 1 to 3 is the biggest increase in disorder. So so again, I've just written here that A has 1 mole of gas on the left and 3 on the right. This is the biggest increase in disorder. Okay, so 22, page 22, we have the units for entropy are joules per Kelvin per mole. Let's have a look at Gibbs free energy. So the Gibbs free energy is, as I mentioned, a way that we can tell whether a reaction is going to proceed or not. So we had a look at the final equation here with the water. We know that this equation definitely proceeds in a forward reaction, okay, because this is actually what powers rockets that go into outer space. Okay, so they have hydrogen gas and oxygen gas reacting together to give water, and we know that's a very powerful driving explosion. And so even though there's a decrease in entropy, so the Gibbs free energy tells us exactly whether a reaction is going to be spontaneous or not, and it considers the delta H, and it considers the temperature times the delta S. Okay, so again, this part here is our entropy. This part here is our enthalpy, and T is our temperature. Also, we have delta G is minus RT natural log of K. K is our equilibrium constant, and we haven't covered that yet, but we will soon. But just know that K is a way of measuring products to reactants. If you had this general reaction, A lots of A, B lots of B, C lots of C, D lots of D, so the little lowercase letters are the stoichiometry. This might be a 5 and a 2 and a 1 or something, and the uppercase values are the species. They go into this equilibrium expression where you have the products, so the species multiplied by the coefficients that are in front of them, sorry, not multiplied, to the power of the coefficients that were in front for the products, and the reactants is the same. So I'm going through this quick, but you can see that it's basically a ratio of the products compared to the reactants, taking into consideration the stoichiometric powers there. But basically, for a delta G that's negative and a delta G you want to have negative for a reaction to occur, then K is always greater than 0. K is always positive. And so that's something that might come up in an assignment and something you want to know, even though we won't go into a lot of detail about what the equilibrium constant is at this stage. So as I mentioned, we're talking about spontaneous and non-spontaneous here, and delta G gives us that determination. The spontaneous reaction creates products from reactants. Non-spontaneous reactions do not proceed. So spontaneity does not indicate how fast a reaction proceeds, but can indicate the amount of products formed relative to reactants. And so a reaction is spontaneous if our Gibbs free energy is less than 0, and non-spontaneous otherwise. So when you hear the term spontaneous, you often think of something that's you would probably think of a fast reaction rate, but that's not the case. Some spontaneous reactions occur very, very slowly. In society, we use the term spontaneous when we're referring to individuals that will do things on a whim, or just be maybe reckless or something. But you can have very, very, very slow reactions that are spontaneous. So all the term spontaneous means is that it's just going to happen, Not that it has to happen fast, not that it has to be spectacular. It just has to occur. So, a reaction like diamond converting back into carbon, almost like coal, is a spontaneous reaction. It just occurs extremely slowly, but it still would be considered spontaneous. It just might take millions of years to get any appreciable amount. Okay, so spontaneous really just refers to a reaction that's going to proceed or not. Okay, so so again, the diamond going into graphite, I should have said instead of carbon, going into graphite is not something you're ever going to be able to witness. But according to the equilibrium constant and looking at that consideration, it would be considered a spontaneous event that would happen over time. Okay, so looking at this, we have our consideration of delta G and delta H minus T delta S. We can see that if we have a negative, again we want negative, if we have a negative delta H, that would help have a negative delta G. If we have a positive delta S, that would also help a negative delta G. The reason is because this minus multiplied by this positive, if this was indeed positive, would give us a negative value. Okay, so if this was positive 2, it would be delta H minus 2, multiplied by the temperature. The temperature is always positive. Okay, so I hope that makes sense. But reactions are favoured by negative delta H's and positive delta S's. This is what you need to think about. So if indeed we have that, where the delta H is negative and the delta S is positive, then delta G has to be negative for all temperatures. If this was minus 7 and this was, the temperature was say 2 and this was, say plus 5, then you'd have minus 7 minus 2 times plus 5, so it'd be minus 7 minus 10, which would be minus 17. You can't have a positive value for delta G if delta H is negative and delta S is positive. Okay, if on the other hand delta H is positive and delta S is negative, then there's no way that you can have a negative delta G. So if delta H is positive and delta S is negative, then delta G has to be positive for all temperatures. Okay, doesn't matter what the temperature is, you're going to have a positive delta G, and therefore a reaction where it's not going to proceed. So in the example with the water being formed from the hydrogen gas and the oxygen gas, that was a negative delta S, but the delta H was so negative as well that it counterbalanced or counteracted the decrease in entropy. And so that would be a case here for this third one. If delta H is negative, so if it releases heat, and delta S is negative, then delta G will be negative at low temperatures, because at higher temperatures, the higher the temperature, the more significant the delta S term becomes. As this changes from 100 to 200 to 300, it's multiplying the effect of the delta S. So if delta S is a negative, which is not ideal, if delta S is a negative, then that means that as the temperature increases, it's magnifying that negative effect, and so the delta H is a certain value. Say it's negative 100, and say this temperature is 2. Okay, and this delta S was say 10 or something, or negative 10. As this one keeps increasing, as the temperature increases, after 20 degrees or 30 degrees or 40 degrees or Kelvin, as it keeps going up, it's going to make this term more significant. Okay, so if you have in the opposite case a positive delta H, which is something we don't want, and a delta S that's positive, which is something we do want, then delta G is going to be less than naught only at high temperatures. Okay, because that delta S is positive is a favourable thing, then the higher the temperature, the more favourable that's going to be, and the more likely it's going to make delta G negative. So I hope I didn't confuse you with that, and it takes a while to sort of digest, and you might want to put in your own numbers on a calculator or something and just think about what it means. But basically, if I just summarise this again, a negative delta H and a positive delta S is perfect. It doesn't matter what the temperature, you're always going to have a negative delta G. If you have a positive delta H and a negative delta S, then it can't work ever. You're always going to have a positive delta G instead of a negative one at all temperatures. If you have a negative delta H, which is a good thing, and a negative delta S, which is a bad thing, at high temperatures it's not going to be negative for delta G, because again that temperature starts magnifying the less than ideal entropy we have. If delta H is positive, which is not a good thing, and delta S is positive, which is a good thing, then delta G is going to be less than 0 at high temperatures, because the temperature is going to magnify the effect of the delta S. It's going to magnify the good thing, and so so I hope that sort of makes sense. The ACS workbook may help explain it better. Okay, so let's do an example. If we have 2.5 moles of a certain salt dissolved in water, so that's 150 mils of water, and the temperature of the solution increases from 13 degrees Celsius to 25 degrees Celsius, we need to calculate the delta H per mole. Okay, so assume the density of solution is 1 gram per mil and the specific heat capacity is 4.75 joules per Kelvin per gram. So we go back to our formula here, Q equals MC delta T. So we have our 150 grams of the solution, the water, 150 grams because we've assumed that the solution is 1 gram per mil. Okay, so I can make that 150 mils into 150 grams. You might want to refresh what density means. Density is mass over volume. So I'll multiply it by my specific heat capacity, which is 4.75 joules per Kelvin per gram, and then I multiply it by my difference in temperature from going from 13 degrees up to 25 degrees. So my final minus initial. And I get this number of joules. Now this is for the 2.5 moles of salt. Okay, so I'll get this delta H, and this is for 2.5 moles of salt. Now here's an important thing. Delta H is always minus the Q. So if the Q is a positive value, it means heat has been released from the reaction. So if the beaker you're working in, the temperature goes up, that's a positive Q value. But remember that temperature in the beaker has only gone up because the reaction has released the heat. So I'll say that again. The temperature in the beaker has only gone up because the reaction has released the heat. So the delta H is always the opposite of the Q in sign. So if this much energy was released, then I have to put a negative sign here, because from the reaction, it's going to be an exothermic reaction in order to release the heat. If it was endothermic, the temperature of the beaker would actually go down. Even though you'd have a positive delta H, you would have a cooler beaker, because remember, endothermic heat is absorbed. Okay, so then I divide my energy by the number of moles I have, and this will give me the joules per mole, okay, which is 3,420 joules per mole. And then I'll just convert that to kilojoules by dividing through by 1,000, and so I have 3.4 kilojoules per mole. Okay, so that concludes the lecture on our energetics. Please make sure you read the textbook and the ACS book, and try and understand as best you can, and contact me via email if any of this is hard to grasp. Thank you.